The PIC architecture has no hardware support for automatically saving processor state when servicing interrupts. The 18 series improved this situation by implementing shadow registers which save several important registers during an interrupt. PIC cores have skip instructions which are used for conditional execution and branching. The skip instructions are skip if bit set and skip if bit not set. Because core before PIC 18 had only unconditional branch instruction, conditional jumps are implemented by a conditional skip followed by an unconditional branch. Skips are also utility for conditional execution of any immediate single following instruction. In general, PIC instructions falls into 5 classes. Operation on W with 8-bit immediate operand. Example, move literal to W and literal with W. One instruction peculiar to the PIC is RETLW, load immediate into W and return, which is used with computed branches to produce lookup table. Operation with W and index register. The result can be written to either W register or the selected register. Bit operations. These takes a register number and a bit number and perform one of 4 actions: set or clear a bit and test and skip on set clear. The latter are used to perform conditional branches. The usual ALU stages flags are available in a numbered register, so operations such as branch on carry clear are possible. Control transfers. Other than the skip instruction previously mentioned, there are only 2: go to and call. A few miscellaneous zero operation instructions such as return from subroutine and sleep to enter low power mode. These are the commonly used assembly language instructions. Performance. Many of these architectural decisions are directed at the maximization of top-end speed or, more precisely, of speed to cost ratio. The PIC architecture was among the first scalar CPU designs and is still among the simplest and cheapest. The simplicity of the PIC and its scalar nature also served to greatly simplify the construction of real-time code. In low-level development, precise time is often critical to the success of the application, and the real-time features of the PIC can save crucial engineering time. A similarly useful and unique property of PICs is that their interrupt latency is constant. External interrupts have to be synchronized with the clock of instruction cycle, otherwise there can be a one instruction cycle jitter. International interruptions are already synchronized. The constant interrupt latency allows PICs to achieve interrupt driven to low jitter time in sequence. The 3-cycle latency is increased in practice because the PIC does not store its registers when entering the interrupt route. Limitations. Only a single accumulator. A small instruction set. Operation and registers are not orthogonal. Some instructions can address RAM and or immediate constant, while others can only use the accumulator. Memory must be directly referenced in arithmetic and logic operations, although indirect addressing is available via two additional registers. Register bank switching is required to access the entire RAM of many devices. The following limitations have been addressed in the PIC 18 but still apply to earlier cores. Conditional skip instructions are used instead of conditional jump instructions used by most other architectures. Index addressing mode is very rudimentary. Stack. The hardware calls stack is so small that program structure must often be flattened. The hardware call stack is not addressable, so preemptive task switching cannot be implemented. Software implemented stack are not efficient, so it is difficult to generate reentrant code and support local variables. Program memory is not directly addressable and thus space inefficient and or time consuming to access. Compiler development. These properties have made it difficult to develop compilers that target PIC microcontrollers. While several commercial compilers are available in 2008, Microchip finally released their C compilers, C18 and C34, their lines of 18F, 24F and 30 and 33 processors. By contrast, Atmos AVR microcontrollers, which are competitive with PIC in terms of hardware capabilities and prices, but features a RISC instruction sets, have long been supported by the GNU C compiler. Also, because of these properties, PIC assembly language code can be difficult to comprehend. Judicious use of simple macros can make PIC assembly language much more palatable, but at the cost of reduction in performance. For example, the original Palarex PIC assembly has macros which hide W and make the PIC look like a two-address machine. It has macro instruction like move the data from address A to address B and add data from address A to data in address B. It also hides the skip instruction by providing three operand branch macro instructions such as compare A with B and jump to test if they are not equal.